So we have a car, pretty simple question. You've done this problem before, initially traveling 20 meters per second east, and then it's going to accelerate to 32 meters per second east, does that in 3.5 seconds. Calculate the average acceleration. So write down what I know and go from there. Initial velocity, 20, east. Final velocity is 32 meters per second east. So no changing direction, nothing crazy happening. This is just practicing our math again. Time 3.5. Calculate the acceleration. The same formula we've been using for a few days. Acceleration is final velocity minus initial over time. Numbers in. 32 minus 20 over 3.5. I think that works out to 3.43 meters per second squared. Okay. So just straight up normal acceleration problem. Part B is something new. This is what we're learning today. Part B is asking us to calculate the object's position. We want to know where it is. That's the power with velocity and acceleration being vectors. It links directly to where the objects are at any point in time, where they are from a reference point, from an origin. Speed, if you're working with speed, you can calculate distance traveled, but it doesn't relate to where the object is at all. If you want to know where something is, we need to know acceleration and velocity. Unless you want to be growled at online. It'll be the first time. All right. So now we're going to calculate the position. Set up our reference system and our coordinates system. So nothing has changed here. We could have done that for part A as well. So west is negative, east is positive. Frame of reference is always the ground, okay, relative to the ground, surface of the earth. We're assuming it's not moving or rotating. East positive, west negative. So reread the question, write down everything we know again. So even if you've calculated something else, we're going to use that 3.43. So writing it all down. So everything, initial velocity, 20. These problems get a little bit faster to do once you get used to the new formulas. Final velocity, 32. Time is 3.5 seconds. Now we have the acceleration, 3.43. Still east. We are looking for final position. What was the object's initial position? 0. Exactly 0. You were not told what it is, so it's just going to take the assumption that it's 0. So if you're not told where an object is, its initial velocity is 0, right? So if no information is given, assume 0. Makes things easier. Now we're checking for a new formula that relates some or all of these variables. So they'll be found in your handbook. So you'll be using this a little more regularly now. And I've just zoomed into the two formulas that we use mainly for finding position. So this formula is at the end of that row under the kinematic section. It incorporates change in position and initial and final velocity and acceleration. And then the other one over here is already solved for final position and incorporates initial velocity and acceleration and time. So the last one does not have a T. So maybe do some problems where we're not given time. We're going to use this one. And later on, I'll show you where we get that formula. It's not one of those formulas that's kind of created from the principles of how motion works. This formula comes out from the math. And so this formula here comes out by doing a little bit of math work. I'll show you that after. Not today, some other day. So there's two formulas. Okay, there's two possible formulas. Each of these formulas will work for this question. First thing you need to know is you do not need to use every piece of information that you are given. Okay, so we're given final velocity, for example, we do not have to use it. Okay? If we're using the first equation, there's no final velocity. It doesn't matter how fast it's going at the end. All that matters is the acceleration, the time, and where it was. If we're using the other one, then we need to use final velocity. So which equation should we use? First one. Yeah. The first one, we'll use this one. Why? Both will work. Think about the math you would have to do if you're solving the second one. What you're looking for is inside brackets. So you've got to put your values in, rearrange your equation, and do some more mathematical steps. The first one, it's already solved for the variable we're looking for. That's the path of least resistance, so let's use that one. So sub the values in and solve for what we're looking for. We're looking for df, final position, initial position is 0, initial velocity was 20, time of 3.5, 1/2, acceleration 3.43, and 3.5 squared. Watch your order of operations. It may have been a while since you've done some math with multiplications and exponents in there. So 20 times 3.5 is going to be 70. All of this, rest of it works out to be 21. There might be some decimal places there. I'm just rounding it off. So the first number, 70, is kind of like how fast it travels if there's no acceleration. So if acceleration was 0, it would be its initial velocity, which would stay constant, multiplied by time, something you did last year, speed times time. Because it's accelerating, it's getting faster and faster. The 21 is kind of like how much distance it gains because it's continually getting faster and faster. So that works out to be 91 meters. It's a positive value, which means it's 91 meters east, which makes sense. Our object did not change direction. It started east, it gained velocity in the east, so it ended up 91 meters away.